Today we will go over section 4.5, which is an algorithm for curve sketching. We will learn how to sketch these curves by integrating the skills we had from chapter 4 as a whole. When sketching a graph, there are some steps given to us to follow. For these ones, it's just the skills we had. First, we determine any discontinuities or limitations when solving it. Second, we determine any vertical steps, and you determine any intercepts. But just reading this out loud, I don't think will do any good to you. Rather, I'll just solve a problem by integrating these steps one by one. So here, they want us to use the algorithm that we saw before for curve sketching to sketch the graph of this fx given to us. The first step we have is to determine any discontinuities or limitations in the domain. So I see that this is in fact a polynomial equation, and I know no discontinuities or limitations are here, so I'm just gonna say no, there are no limitations. So we're good to go for the second step, which is to determine any vertical asymptotes. Again, I know vertical asymptotes occur when I have a form p equaling to, let's say, like qx, and I forgot what they put, but let me just say cx, right? That's what I mean when it's in a rational form. That's when I find the vertical asymptote when the denominator equals 0. This is again a polynomial, so this is not affected, so I don't have any vertical asymptotes either. So I pass on to the third step, which is to determine any intercepts. So I know x-intercepts occur when y equals 0, right? So I'm just gonna equal my equation to 0 to find that. I see that from here I have a common factor I can take out, which is x, but to make it easier, I'll just take negative x out. From here, I'm gonna find the roots of 3x squared minus 2x plus 5, which is inside the bracket. When I do that, I'm gonna get 3 values. So those 3 values would be negative x equaling to 0, 3x plus 5 equaling to 0, and x minus 1 equaling to 0. From here, when I divide each side by negative for the first one, I'm going to get x equaling to 0. I'm going to send that 5 to the other side as negative, so that would give me 3x equaling to negative 5. And I'll divide it by 3 for each side to get a value of negative 5 over 3. From here, I'm just going to send that 1 to the other side to get a value of x equals 1. So from here, I can also determine the coordinates of this. Since my x equals 1, I'm just going to put in the place of x1, and the place of y will just become 0 because that's exactly what we were trying to find. Over here, the same thing, my x value is 0 and then my y value is 0. Same thing over here, my x value is negative 5 over 3 and my y value would be 0. So I found the coordinates where my graph intercepts the x axis. In terms of y-intercept, I know it occurs when my x equals 0. All I need to do is plug in x equals 0 to my function, and when I do that, this will equal 0, this will equal 0, and this will equal 0, so I get a value of y equaling to 0. So my coordinate for that would be 0, 0 as well. Now I'm going to go ahead to my next step since I found my intercepts, which is determining any critical numbers by finding where my derivative equals 0 or when my derivative is undefined. My first step would be to find the derivative of my function, which I'll apply the power rule to find that. So when you apply the power rule, again, I kept the constants over here. This power comes to the front and you do minus 1 to the power and I get negative 9x squared. Same thing over here, I keep negative 2, bring that 2 to the front, which will give me negative 4 when multiplied. And I have 1 over there, and over here x to the power of 1 will just become 1, so I have the constant plus 5. Over here, now what I'm going to do to find the critical number is equal this to 0 like said, and over here I can just take out the negative to make it easier on me, so that would just give me 9x squared plus 4x minus 5, and from here I'm just going to find the roots, which will give me negative 9x minus 5, and then x plus 1 equaling to 0. Now from here I can equal 9x minus 5 to 0 as well as x plus 1 to 0 to find the roots. I'm going to send that 5 to the other side to give me 9x equaling to 5. Now I'm going to divide each side by 9, which will give me 5/9. So that's 1. And over here, I'm just going to send out 1 to the other side to get x equals -1 value. Now that I have my critical numbers, the next thing I'm going to do is determine the intervals of increase, decrease, and then test critical points to see whether they are local maxima, local minima, or neither. What I'm going to do first, because it's easier, is to determine my local maxima, local minima, or whatever by using the critical points I found, because it's easier. All we need to do, like we did before, we can just plug it into our original function to find which one is maximum and which one is minimum. So when I do that, I get the value of -4 for my -1, and I get the value of 1.65 for 5/9. So because the largest value I have is 5/9 with 1.65, this is my maximum, and I know my lowest value is -4 with -1, so that would be my minimum. So when I separate it into intervals to find if it's increasing or decreasing, which is the portion where it says determine that, I'm going to start with x smaller than -1, because remember when we draw a graph, if one of my critical numbers is -1, which is here, and the other one is, let's say over here, like 5/9, I need to figure out what happens to my function before it reaches -1, which is when x is smaller than, and I need to figure out what happens between, which I'm going to put as another interval, so -1 to 5/9, and I need to figure out what happens after 5/9, so when x is bigger than 5/9. Now I'm going to plug in these values into my derivative to find if it's increasing or decreasing. If, let's say for this interval, I'm just going to choose -2 to not make it bigger, and I get a value of -23, which is, since it's negative, I'm just going to put the negative sign because we only want the signs that indicates if it's negative or positive. For between -1 and 5/9, I'm just gonna, because I'm plugging into my calculator and I know 5/9 equals 0.56, that's the value, I'm just gonna put 0.2 or 0.1 even. Let me put 0.1. If I do that, I get a value of 4.51, which is a positive value. Now I pass on to the other one. Here I'm just gonna put 1 because it's easier. When I do that, I get a value of -8 for this when I plug in 1. So that's only negative sign. So from here, I can see in terms of the behavior, if it's increasing or decreasing. I know it's decreasing over here when it's smaller than -1. It's increasing over here, and it's decreasing again over here. Now I need to figure out what they want me to do next, which is to determine the behavior of the function for large positive and large negative values of x, and this will identify horizontal asymptotes if they exist, and identify if the function values approach the horizontal asymptote from above or below. Again, like we did before as vertical asymptote, this does not have horizontal asymptote because it's not rational, it's a polynomial function. So because it doesn't have a horizontal asymptote, we can just say no horizontal asymptote, no vertical asymptote. I'm not going to write it, but I'll just skip it. The second one is to determine the second derivative and test for points of inflection using the intervals of concavity. Now the first thing I'm going to find is the second derivative, which I already found the first derivative, so that would be just taking the derivative of what I have as first derivative. When I do that, I just apply the power rule, and I get a value of -18x -4. Now, in order to find my point of inflection, I need a point, which I can find by equaling my second derivative to 0. That would give me -18x equaling to 4, and I will divide each side by -18 to get a value of -4/18, which I can simplify it into -2/9. Now I'm going to base my intervals to this point. So since my point is -2/9, the first thing I'm going to put as an interval what happens before reaching that point, so when it's smaller than -2/9. Now I'm going to figure out what happens at that point, if it's actually my point of inflection. I need to confirm that. And I also need to figure out what happens after that point, so when it's bigger than -2/9. So starting by plugging in values to my second derivative to find if it's concave up or concave down and point of inflection, I'm going to choose a smaller value than -2/9 for the first one. I know when I plug it into my calculator, if it makes it easier for you guys, that equals a value of -0.22. So I just need to find a value that's smaller than that. So for me, I'll just plug in -1 because it's easy. If I plug in -1 to this value, I'm going to get 18, positive 18 minus 4, which would give me 14. So I know this is positive. Now I'm going to pass on to -2/9, which will just give me 0. We already know that. And a value that's bigger than -0.22, which I can just put 1, right? And that would give me a negative value. So from here, I can actually see, because I change my signs from positive to negative, this is in fact my point of inflection. And I know for the first one, because it's positive, this is concave up. And because this is negative, this is going to be concave down. So it's going to look something like this. The next point I have is determine any oblique asymptotes, identify if the function values approach the oblique asymptote from above or below. I know oblique asymptote occurs when the numerator degree is higher than the denominator degree. Again, this is only a polynomial function and not in the form of like px versus qx, like px over qx. It's not in that form, so I don't have oblique asymptotes either. So I'm just going to skip this and say, no, I don't have oblique asymptotes. My last step is to complete and sketch using the informations I've gained. First, I'll start with putting my x-intercepts in there. I know my x-intercept occurs at right over here. Yeah. I also know, so I finished this, I also know it occurs at 1. And I also know it occurs at -5/3. And if I plug it in, if it makes it easier for you guys, -5/3 equals -1.67. So I'm just going to put it right over here. So that's also my x-intercept. Now my y-intercept also occurs right over here, so I'm not even going to put anything because I already plotted it. Oh, that wasn't reason. Now I know my maximum point, passing on to critical numbers, my maximum point occurs when x equals 5/9, which equals 0.56, so around right over here, let's say. However, I need to find also the y value of this, which I already found when I plugged it in, and that was 1.6, which I can put it, if I put 1 over here, and if this is my 2, my 1.6 would be right over here. So I'm just going to put these two values over here to get my point of maximum, which would occur right over here. So that is my maximum point. My other point occurs at -1, and when I plug it in, I know I get a value of -4 for the y value. So since my -1 is over here, -4 is over here, my minimum occurs right down here. I know this is my maximum, so I'll just local maximum, so I'll just label it, and I know this is my local minimum, so I'll just label it to make it easier. Now from here, I'll start by what happens smaller than 1. Right? I'll just check the intervals now. I know my interval decreases when it's smaller than 1. So all I'm going to do, because it decreases to my minimum, and I have to pass this point also, I'm going to put a line that decreases and goes to my minimum. Now, because I did this interval, I know what happens between -1 and 5/9, which I know 5/9 is right over here. However, I also need to take into account what happens before my inflection point, which is -2/9. And 2/9 corresponds to -0.22. So I'll just put that in. So -0.22, so it would be right over here, right? And if I check it from here also, we said this was concave up, so it makes sense why I'm coming from over here and going down, because if you think about it, like just think about half of this, that's what I'm drawing. So I also satisfy this one, so I'm just going to cross that out. What I'm going to do now is just put a point of inflection at -2/9 before increasing. And to also get a value of when this point of inflection occurs, what's the y value of it, all I'm going to do is plug in -2/9 to my function to get a y value. When I do that, I get a value of -1.2, which should be like right over here. And when I put that together, my point of inflection occurs right up here. So I'm just going to connect the dots and go to my max, because I know it's the point of inflection I put it on, and I just need to increase until 5/9. So when I do that, this is my minimum, go to my point of inflection, and then go to my max. Now from here, I need to figure out what happens after 5/9, which is mentioned over here, as well as what happens after -2/9. So that's why when I came, I'll draw that again, you might not be able to see it. When I came, I did concave, I did increasing, but I need to make concave down after -2/9, which just think of it as half. So I'm gonna draw this portion, so when you start, you would put something like this, if it makes sense. That's too much, but just to show you that it's actually concave down. So I just start going like that. Now from here, all I need to figure out is I satisfy this. I need to figure out what happens after 5/9, which it says it decreases. So I'm going to decrease to my Xintercept, and when I do that, it's just going to go like that. And I can put my arrows for these. And for some problems, they would want you to specify the maximum coordinates, minimum coordinates, and point of inflection coordinates. So it's better to get used to actually putting them on whenever you draw a sketch. But that basically is for my whole problem. It is long, so I would just suggest practicing until you get used to it. For this one, I will just put the explanation given by your Nelson textbook, but it is the same exact steps. The only different part is over here. Now I will probably have vertical asymptote and a horizontal asymptote because it's in a rational form. So the first step, as always, is determining any discontinuities or limitations in the domain. But when I do that, I don't get any discontinuities or any holes whatsoever in my graph. The second step is determining vertical asymptotes. When I do that, the only thing I need to do is take the denominator, equal that to 0 to find out if there's any vertical asymptotes at any point. And they do in fact found there are vertical asymptotes at x equals 2 right over here, and then x equals -1. They also examine the values near the asymptotes to find out if it's approaching positive infinity and negative infinity, which we did before. The third step is determine any intercept. In this case, they do the same thing. To find the x-intercept, we need to equal y to 0. For y-intercept, equal x to 0, and you would get the values of 4, 0, and 0, 2, which will help me to sketch my graph. My next step would be determining any critical numbers. In this case, we need to take the derivative and equal it to 0, or if it's undefined at any point. When they take the derivative, they get this as a function, and then they equal it to 0 to get a value of 4 plus or minus root 10. And then they get the approximate values, which is 7.2 and 0.8, which are acceptable, and they get values for critical numbers. Now the next step would be to determine the intervals of increasing or decreasing, and then by testing the critical points, we need to find the local maxima or minima. Over here, when they put it into intervals, they get these values. If you want, you can pause it and solve it. Also, if you want, you can just solve this by yourself and then check the solutions from here too. That would be really effective. And these are the intervals that they found. They found decreasing, decreasing, increasing, increasing, and decreasing. The next step they did is to determine the behavior of the function for large positive and large negative values, and this will identify the horizontal asymptote. This is a different part from the previous question because we didn't have a horizontal asymptote. So what they did is they did find a horizontal asymptote at y equals 0. We did go over how to find horizontal asymptotes. If you're not familiar with it, you can watch our video on horizontal asymptotes. And if you plug in a very big positive value and a very small value such as like 1000 and negative 1000, which we did before too to figure this out when we were sketching in chapter 4. So if you're again not familiar, I would suggest you watch that, go in detail, because these skills build up. And they found that the curve approaches from above on the right and below on the left. And from here, this other step is determining the second derivative and test for point of inflection. You can do that by the same thing that we did. They didn't do it because it gives you enough information, really. So I'll just skip that, but you can again do that. It's not very hard to do. You just take the second derivative and see if it's changing from concave up and concave down. You can refer back to the previous question and how we did it. And the next step they did is to determine any oblique asymptotes. From here, I see that for my numerator, for my numerator, I have the value of 1, and for my denominator, I have the degree of 2, right? Degree of 1 and degree of 2. I know oblique asymptotes occur when the degree of the numerator is bigger than the degree of denominator, but in this case it isn't. The degree of the denominator is bigger because it's 2, so I don't have any oblique asymptotes either. The last step is to actually complete the sketch, and if you do that, you'll get this. Again, we did put our vertical asymptotes over here by given. I know my horizontal asymptote occurred right up here. And we did put the values such as like minimum and maximum like right over here, and yeah, that's it. So if you have any questions or problems you would like us to solve, you can always go to our website, to our forum section, and if it's related to this video or even if it's related to any problem that you couldn't solve, you can always send it to forum section where we will send our responses.